Okay, hello everyone, I'm Tianhao. Today I'm presenting robotic safety with neural network components. So let's first take a look at a typical robotic system, which is composed by a sensor, perception, control, and model. And with full knowledge of the robotic system, we can give theoretical guarantees of the safety. However, with the development of deep learning, more and more components are replaced by neural networks. And ensuring the safety of a robotic system with neural network components is still challenging. So my research focuses on providing guarantees for different neural network components, such that the safety of the system is preserved. So to address different models with neural networks, we propose different methods. We propose online verification for neural network perception module, and we did a study on safety shield for the neural network controller. And we also studied how to do the safe control with neural network dynamic model. Let's take a look at them one by one. First is the neural network controller. So to ensure the safety of the neural network controller, we can append a safety shield after the controller. A safety shield finds a safe control based on the reference control given by the neural network, but it ensures the safety. For example, here, assume an autonomous car is controlled by a neural network controller. Before the safety shield, it may give the control and it collide with the obstacle. But after the shield, the control will be saved. And most safety shield use an energy function. Intuitively, an energy function adds a repulsive force from the obstacle to the control to ensure safety. This is an inaccurate description, but it kind of gives you the idea of how safety shield works. However, the connection and difference of existing safety shields are clear. Here shows an example of two different shields. The blue one represents one safety shield, and the green one represents another safety shield. We can see they both ensure safety, but the green one is more efficient. Although the most safety shield uses an energy function, we still don't know which one is better and how can we design a better one. So we unified most existing methods with a mathematical framework. And with this framework, we reveal their connections and difference. And we can design a better safety shield that beats existing ones on different tasks. Here are the experiment results. We showed the results for different tasks, ball robot, unicycle, Ascara, and robot arm. Here, the x-axis is the safety score, and the y-axis is the efficiency score. If a curve covers another curve, it means it's better because it can achieve a higher efficiency score under the same safety score. As you can see, the purple curve, which is sub-level safe set, safety index we synthesized based on the framework, achieves the best performance on most of the tasks. Next, let's take a look at the neural network model. Designing the safety shield requires the model inverse, such as inverse kinematics or inverse dynamics. However, it is difficult to get a model inverse with the neural network model. And neural network model is widely used in model-based reinforcement learning and to predict how things will change in the environment or how the robot will react to a control input. And even if we have a safety shield for the neural network model, and finding a control that satisfies the safety shield is still difficult. And the most popular controller for neural network model is random shooting, which just shoots many controls and rule out with the neural network model and chooses the one with the best performance. However, this method is lack of optimality guarantee and safety guarantee. And in this example, the autonomous car randomly chooses many control inputs and use the one has the least tracking error with the desired trajectory. However, all these controls are unsafe. They all collide with the obstacle. And even the best control still is far from the desired trajectory. So we proposed a method called mine-sys. The sys part will automatically synthesize a safety shield that guarantees safety. And mine encodes the neural network dynamics control problem as a mixed integer programming, and it guarantees to find the optimal control. So in our experiment, the left figure shows how sys synthesize the safety index, ensures the safety while other shields fail. Here, this phi L is the safety shield synthesized by sys. It achieves a 100% success rate. But for the original safety shield and a manually designed safety shield, they all have failure cases. And the red table shows mine achieves the optimal control, which is a significant improvement compared to other methods. Here, the mean is the mean tracking error, and the STD is the deviation of the error. As you can see, mine achieves an error less than 10 to the minus 8, while a shooting method with even 10,000 sampling size achieves an error of 0.012, which is still quite large. And in the last, we want to introduce online verification, because deep learning-based computer vision has been widely applied to robotic perception. However, the reliability of these perception networks is suspicious. For example, for image classifier with some random noises, it can easily misclassify an image into a totally different kind. And for an object detector, so here is an invisible horse, and this is another invisible horse. And to prove the robustness of neural networks, verification methods were proposed, which can verify whether a neural network satisfies some user-given properties for a certain input range. Here is an example. For example, if you want to verify a digit classifier is robust to perturbations, we can have, so given an input image of a digit 8, we can represent all potential perturbations using a hyperrectangle. And then we can verify whether the output of the neural network always falls into a range. It means whether the neural network always can predict the image with perturbations as 8. So we can use these verification methods to prove a neural network is robust. However, verification methods are super slow, and they are designed for offline use only. But in reality, there are many cases that requires online verification and real-time verification. For example, for an autonomous driving car, you have an object detector, and the input of the object detector is constantly changing with time. If you want to make sure the object detector is safe, you need to constantly verify it on the current image, because it's impossible to verify all potential images in advance. So you have to do it online. But if you want to do it online, you need a real-time verification method. And the red figure shows an example of robot learning. In the case, the robot may have a motion prediction network that predict the motion of other objects. And the robot is constantly learning through interacting with the environment. Although the input may remain the same, but the network is constantly changing. And once the network is changed, you need to verify it again, which also requires real-time verification. So in short, verifying neural network in robotic systems requires significant acceleration of existing methods, from minutes to milliseconds. So we propose online verification. The core idea is leverage temporal dependencies to accelerating existing methods. A very intuitive idea is the input and the network weights both change gradually. Nothing happens in a sudden. There are many common parts we can reuse to reduce the computation time. So we proposed 3 acceleration principles and derived 5 techniques from these principles. And these techniques in combined can accelerate existing verification methods up to 2 orders of magnitude. So here in our experiment, we tested on 3 different scenarios. And for each scenario, we did an ablation study of these techniques. As you can see, with the techniques, the computation time is greatly reduced comparing the baseline, which didn't use any acceleration technique at all. So it's worth noting that the online verification can also be used for neural networks, controllers, and the models, as long as you can give a specification of the networks and the properties you want to verify, and verification method supports that specification. So with all these methods, we can greatly improve the safety of the robotic system with neural network components. But there are more to do in the future, such as how to apply online verification to larger chains and how to synthesize safety shells under uncertainty. And that's the work I will do in the future. Thank you.
Okay, thank you, Tianhao. Now let's move on to the next speaker, Ruixuan.
All right. Can you guys see my screen?
Yes.
Okay, awesome. So hello, everyone. My name is Ruixuan, and this my topic for today's presentation is towards safe and efficient human-robot collaboration. So this presentation is like an overview or like a recap of my thesis work in the past, and also a discussion of my future work that I'm gonna continue working on. So this is a outline of this presentation, and because this is an overview of my recent and future works, I will not discuss the details of the theories and methods, and I will mainly focus on what we have now and discuss what is still needed in the future. So let's get started. So the motivation of this, my research, is that human-robot collaboration becomes a hot topic and has been widely studied. And it becomes more and more important because robots are now everywhere in our life in different forms. So one common thing for all these different robots is that they share the environment with us and need to coexist well with humans. And we allow and want these different forms of human-robot coexistence because robots are more capable in certain tasks than humans. And we want to facilitate the collaboration to achieve better efficiency. So for example, we have autonomous driving cars that run on city roads and highways, and they share the roads with other users like human drivers and pedestrians. And we want these collaboration because they can drive more safely and efficiently than human drivers. And if they can collaborate and share the roads well with humans, and so then we can achieve better traffic efficiency that reduces many traffic jams and accidents. And on the other hand, we also have large industrial robots in factories that do polishing and grinding tasks for humans. And we want these industrial robots because they are good at like heavy duty tasks. And polishing and grinding by humans is very time consuming and potentially dangerous. And if we can replace it with robot workers, then we can achieve better polishing efficiency and reduce manufacturing accidents. And also we have on the right this relatively smaller size collaborative robot that learns how to help people in daily tasks. And the collaborative robot shares the table and other things on the table with the human user. And we want these collaborative robots because they can help handicapped people to do things more easily. So in this case, how to have robots safely and efficiently collaborating with humans becomes a critical research question that I'm currently trying to address. So we start from thinking about the application scenarios that humans can benefit from facilitating HRC. So in our research, we mainly focus on the collaboration between the human and the robot arm. And we mainly consider two potential applications here. One is robot handover, and the other is human robot co-assembly. So here is an example use case of the handover scenario. So in this application, we assume that the wanted object cannot be easily reached by the human. So therefore, we will use the robot to help the human to get the object. So here the human uses hand gestures to tell the robot that he wants the scissors and wants the green one. And then the robot grabs the scissors and hand it to the human. And also notice that more importantly, the robot should hand over the scissors in a appropriate and safe way, which means it cannot approach to the human with the sharp side towards the human. And we can see here in this video, we want the robot to place the handle properly aligned with the human's palm so it can safely hand over the scissors to the human.
Yeah, to be honest, I'm like actually
Yeah.
surprised that most of
And on the right,
Yeah, so there's some background noise, and maybe you can try to get a earphone or.
yeah, I'm using an earphone. Sorry about that.
Yeah, it's fine. It's just it will also be recorded.
Okay, yeah, I'm sorry about that. Yeah.
Okay, go ahead.
That's remote working problem. So on the right, it's another example use case of the co-assembly scenario. So we want the robot to help the human assembling a desktop in the video here. So initially the human is looking for the component he wants, and he might move around to search for it, and the robot needs to safely avoid collision with the human. And then in this case, when the human decides the piece and then pick up the piece to do the assembling, and then as the human is assembling, the robot can grab the next piece and hand it to the human. So in this case, the collaboration can improve the assembling efficiency. And here we only show these two application scenarios, but there are actually a lot more. And for example, we can also extend this electronic co-assembly to other assembly tasks like Lego assembly that I did for my master's thesis. So it is actually an open question that what applications can benefit from HRC, and that's also something we can think about in the future. And with the applications in mind, we can then think about how to build the HRC system. So here it's a modularized pipeline of what we believe are the required modules for the system. And we have four main modules here: perception, prediction, and planning and control. So given the environment information, it can be the human is doing a assembly task, or that the human is giving gesture commands. Then the perception module captures the information, and then the prediction and understanding module interprets the environment information and makes decision of what the robot should do. And then the planning module plans safe and efficient motion trajectory for the robot to do the task. And then the control module controls the robot to do certain actions to achieve the collaboration. For example, here the robot hands the scissors to the human. So then I'll discuss the each of the module and what we have for each of the module. So as I just mentioned, the perception module needs to capture the environment information, and it needs to know what are the objects that it is going to interact with. And these objects includes the both the human subjects and the workpieces that it is allowed to manipulate. And in addition, it also needs to understand the poses of the workpiece in order to know how it can manipulate them. And there are a lot of existing works that address the problems, and we found these approaches quite sufficient in our case. So for example, we use open pose library to detect the human subject, and we can then infer the pose and behavior information of the human. And here we mainly interested in the upper arm motion. So therefore, we can use OpenPose to extract the motion profiles of the arms. And we use YOLO, you only look once, to detect the workpieces that are allowed to touch by the robot. So for example, this human is doing Lego assembly, and the Lego pieces on the table can be touched by the humans, but by the robot. And the YOLO detects the pieces on the table, which are shown by the red bounding boxes here. And we also use point cloud registration to understand the poses of the pieces. For example, here we have a point cloud captured by the camera showing blue and the CAD model showing yellow. And by point cloud registration, we can infer the pose of the workpiece relative to the robot and then decide how to manipulate the objects. So the second module is prediction and understanding. So we want to predict the human motion trajectory in order to avoid potential collision. So we developed an online adaptable arm motion prediction framework for motion prediction. So this framework uses neural network to predict the end effector motion and then use model-based inverse kinematics to extend the wrist motion to the arm motion. And the online adaptation adjusts the performance, the model performance online. And here we still use the Lego assembly case, and we have the prediction showing red dots and the ground truth showing blue dots. And in addition to the motion prediction, we also want to understand what the human is doing and what the human needs for his task. And this understanding improves the quality and efficiency of the collaboration. So we developed an iterative adversarial data augmentation for training robust neural network-based intention prediction. So using the same Lego assembly example, here we output the operation type of the human motion. Either he's assembling, reaching to a piece, or retrieving a piece. And we also predict what is the next wanted piece by the human, which is indicated by the numbers on the bounding boxes here. And then the goal for planning and control is to plan safe and efficient motion trajectory to do the task and safely execute the motion using the physical robot. So we mainly use convex feasible set algorithm and iterative convex optimization for robot motion planning. And here the animation shows the robot executing a planned trajectory. And the advantage of our planning algorithm is that it can efficiently plan and handle dynamic obstacles. So a brief recap of the pipeline. So we apply and adapt existing state-of-art approaches for perception, and our research mainly focuses on the bottom three modules. And although it seems we pretty much have everything needed for each module, there are still a lot of future works that need to be done. So first, for the prediction and understanding module, because of the COVID pandemic, the existing methods were validated on a very limited data set. So due to, we need to collect more data that corresponds to the applications we design and for testing and validation purpose. And also there are a lot of research questions for motion prediction. For example, how good is online adaptation, like how to tune the parameters to achieve the optimal performance, and also what's the performance difference of using different network structures. And in addition, there are many research questions for intention prediction. For example, like how good is our iterative adversarial data augmentation training? Does it have like theoretical performance guarantees? And also another very important thing is that how can we scale the method to larger and more complex neural networks? And also, can we reduce the human effort in the training process? And also another research question is that it is very interesting to kind of combine the motion and intention prediction together to improve the prediction performance. And there are also many questions for planning and control. So the major question is that how do we apply or adapt the existing methods to the desired applications, including the different hardwares and also different prediction outputs. And lastly, we will need to apply the existing methods to the real robots that can help humans. And that is all my presentation. Thank you.
Okay, thanks, Ruixuan. I think we can move on to the next presentation from Hooray and Alvin. Yeah, as a reminder, we'll leave all the Q&A to the end, and if you have any question, you can type in the chat. Cool. So you can turn and Alvin, you can take it over.
Right. Can you hear me?
Yes.
Right. Cool. Right. Hello, everyone. My name is Chen. Today, Alvin and I will be talking about our recent work, the real-time collaborative robot handling with recurrent encoder-decoder attentive neural process. As a background, as an advancement of robotic technology, robots are getting out of the cage and start to work with human directly. Here we focus on one immediate application, which is collaborative robot handling, where the robot moves or presents a workpiece in a specific location and orientation under human commands in real time. Such application is particularly useful when the object to maneuver is heavy or contain dangerous chemicals. People can also use it to boost productivity. The key to making a collaborative robot useful is the wise choice of human interface. First, we have the classical devices such as keyboard, joystick, or teaching pendant. But using those devices can be tedious for complex tasks and require programming expertise. We also have the natural user interfaces, such as hand gestures and vocal commands. Those things are more intuitive and correspond to actual practice in physical world and needs no or less technical skills to use. So in this project, we choose dynamic hand gestures as our human interface. Then the expected robot handling operation can be mathematically formulated as general rigid body transformation. Note that in some applications, such as inspection or welding, the human workers might need to continuously maneuver the object for different positions and orientations for better visibility or working angle. So the robot is expected to be able to respond to continuous and real-time human commands continuously. Here's an example of the use case of our task. So in the animation on the right, the human hand is shown as orange dots shown in the bottom part. And on the top, the object is represented by a coordinate frame that is bounded to the QR code that is attached to the object. So in this task, whenever the human is rotating his hand around the green axis to the left, the object is doing the same similar motions. Here's another example of the use case. In this example, the user is pushing the object forward while moving it upward a little bit. And there's also a rotation with respect to the the red axis. So we can see that in both cases, the human users are mimicking the object motions with their hand motions. And you might notice that in both examples, in the screenshot, you can see that the object is maneuvered by a coworker, since the coworker is demonstrating the expected robot operations in the training data collection phase. Now you have seen two use examples of our framework, and you might start to wonder what other robot operations are supported. And in fact, in this work, we plan to support any robot operations that can be formulated as a rigid body transformation. And to make this possible, there are some key questions to answer. The first one is, in general, how should human use their hands to control robot operations? And in this work, we actually teach each human with an initial gesture strategy, and the users are free to adjust until they feel comfortable about their policy. Experimentally, we verified that providing insufficient instruction would actually burden the users with cognitive and physical efforts to develop their policy from scratch instead of bringing more freedom. The other question to answer is that for an arbitrary complex object motion trajectory, how should a human achieve that using their hand motions only? And this work, we actually recommend each user to use multiple motions with respect to dominant directions instead of reaching every complex motion in one shot. Here, the dominant directions are directions such as forward, left, and up and down, which are easy for human to parse and understand. And experimentally, we also show that decomposing the general rigid body transformations and controlling using finite and easy gestures is actually easier for people than telling them to work out a single hand gesture or arbitrary complex motion. Next, I will talk about some existing approaches for gesture-based robot applications and why they show limited capability in our case. First, people have been mapping predefined static gestures to robot behaviors. And this method doesn't apply to our case because there are infinitely many possible handling operations as in rigid body transformations. The other approach is to map predefined dynamic gestures to robot behaviors. This method does solve the continuous action space problem, but it doesn't adapt to user preferences or noisy sensing system. Specifically, in the event that part of the hand that is essential to the robot operation is missed by the perception system, the robot task will fail. In summary, there are two challenges in our task. The first one is the adaptation to different user styles. For example, some workers might prefer to rotate their hands in place, and some others might prefer to rotate their hands while moving the whole body. The other challenge is being robust to noisy human input. Even with the most advanced motion capture system nowadays, it's still possible that the perceived human body pose and hand gestures are jittering, incomplete, or noisy. And for safety concerns, the model needs to be able to still generate reasonable motions and safe and smooth motions, even if the natural human input is not. And next, I'll leave it to Alvin to talk about our current approaches and how each model feature solve these challenges.
Right. Can you guys hear me, by the way? Yes?
Yes.
Yeah. Okay. Yeah, let me share screen. Okay. So Ray mentioned the two challenges that we are trying to address. And here is our overall proposed approach. First, we're given some new hand motion sequence from some user that we want the model to interpret. And we want the model to generate the corresponding object motion. This hand motion is defined as a sequence of finger and hand velocities, 3 dimensions for translation and 3 dimensions for rotation, where in total there are 5 fingers and the palm. At the same time, we're also given some pre-recorded data, which we'll call context. And here, this context data contains not only hand motion, but also ground truth object motion, where the object motion is defined as 3 dimensions for translation and 3 dimensions for rotational velocity. The overall purpose of this context data is to capture some initial style of that specific user. And you can think of this as like a calibration data. So we process both context and this target data in some recurrent model that loops over the time steps. And it's composed of 2 components. One, the hand motion encoder, whose purpose is to extract features from the finger and hand velocities. And second, the decoder, which interprets these finger hand features and generates the corresponding predicted object motion. Now I will go into detail about these 2 modules. First, we have a hand motion feature extractor. And we implemented an attention over finger module, where the model can place a weighted sum over all these different fingers. So in this picture, in this video, you can see that the different fingers, as well as the palm, are represented by different colors. And the colors correspond to the weights associated with them. Green means a lower weight, and orange or yellow corresponds to a higher weight. And you can see throughout the video sequence, these weights on these fingers change. So some intuition about these are first that different fingers can vary in usefulness for understanding a certain hand gesture. Maybe a user only focuses on certain fingers when they are trying to control the object, but other fingers they don't really focus on. At the same time, certain fingers can become occluded as the hand rotates. And by introducing this attention module, the overall model can adapt and pick whichever fingers are the most valuable for interpreting the hand motion. Second, we have a recurrent decoder model. And this is composed of 3 key parts. And first of all, the first challenge that Ray mentioned that we're trying to solve is noise in the human hand motion data. And this recurrent model's goal is to introduce a time dependency between the outputs at previous time steps. So here, what we mean by that is we feed in the previous time steps object motion, denoted by y of t minus 1, into the model. And along with that, the current time steps hand motion, denoted by x of t. And what we're trying to do is predict the object motion at the current time step, denoted by y of t. And so the first part of this recurrent model, the overall goal is to introduce robustness to noise in the human hand motion data. So even if the current hand motion, the current time steps hand motion is noisy and contains spikes in velocity, the corresponding output of the model should not be noisy, but should be consistent with previous time steps outputs. And so a key component of training this is a technique known as teacher forcing. As you can see in this diagram, initially during the training phase, we always choose the ground truth previous object motion, denoted by this green box. And what this does is it helps the model to learn to become dependent on the previous time step. And this way the model learns a short-term time dependency. But as training progresses, the probability of selecting the ground truth as this previous object motion should decrease. And rather, the probability of selecting the model's own previous output should increase. The reason for this is that the model should not always assume that the previous time steps object motion is correct and is true, but should be robust to errors in that previous prediction. This overall helps the model learn a long-term time dependency, where the current time steps prediction not only depends on the previous time step, but also multiple past time steps. Second, another problem that Ray mentioned was how can we adapt to new users and new human hand gesture styles? The context attention, denoted by this box in the figure, is a key aspect of that, where we have some initial calibration context data that doesn't necessarily capture all possible hand motions, but is mainly meant to capture the overall, contain the specific style of that user. And by attending over this context, we can infer from this human style and apply that to interpret new unseen hand motions. Next, here is a video of the model's performance. So as you can see in this video, the long axes here, the long coordinate axes denote the model's own prediction, whereas the shorter axes denote the ground truth. And you can see that our model's prediction closely matches the actual ground truth. Some issues you might notice are that there's a slight delay in the object's own prediction. And these are possible things that can be improved on future works. And now we can take questions if there are any, and if there's any time. But if not, can move on.
Yeah, we'll leave the Q&A towards the end. Thanks, Alvin and Chen. We can move on to the last presenter, Letian.
Oh, yeah. Can show my screen. Yeah, hi everyone. I'm Letian. Today I'd like to share you with our recent work, hierarchical, adaptable, and transferable networks for driving behavior generation. First, we have some simple background, especially on the learning method. And we know learning method has been pretty popular these years. And what can it do now? It actually can do pretty well, actually. Especially, it can beat best human chess player, play archery game from raw pixels, and control robots in simulation and real worlds. But there are actually one kind of a specific task. And what they cannot do very well currently is that it cannot, when the learned policy are facing new tasks, we cannot answer two questions. First is that how can we use the knowledge we have learned before? And second is that how can we deal with the tasks that we have not seen before? And to solve these two questions, we actually can turn to humans, because humans are actually neural networks that has learned or evolved for thousand years. Then what can we learn from humans? Actually, we can learn a lot, such as psychology, sociology. But today, I'd like to show you our research on the cognition model, specifically the hierarchy. On the right, we can see human society or humans' behavior are naturally divided to hierarchies. We can see different hierarchy in sociality and society, and also we can see the baby when it's accomplishing one task, it actually divided into various different subtasks, such as approaching, picking, stacking, and leaving. Then such kind of hierarchy seems very common in our life. Then how can they help with learning? Actually, it can help a lot. Firstly, they can do the information filtering. It's actually solve the problem of the curse of dimensionality. It is because that when we have the hierarchy, each hierarchy only handles its own subtask, so that they only need to care about the state that is relevant to the task. So the state representation is reduced, so the learning can be much more faster. And the second is that it can be much more transferable. It is because that when one hierarchy policy learns very well on its own subtasks, the policy can be used in multiple tasks or new tasks. Yeah, and this is most helpful, especially in the imitation learning method. And also we have some other benefit, that is long-term credit assignment or the structured exploration. They basically benefit the reinforcement learning field. And today we are only trying to leverage the first two benefits. Then we'll dive into a specific scenario. We can see in this video that when humans are driving, it's actually very complex or even difficult task, especially in the video, everything goes things like crazy. But actually human can do pretty well in this task. How did it do that? Actually, when each car are entering the intersection, it actually only cares about which area the car can insert into. And with this intuition, the representation about the complex state can be very reduced. And also such kind of mechanism is also very transferable and adaptable in different scenarios and different individuals. Yeah, consider, and with this intuition, we proposed a hierarchical, adaptable, and transferable networks for the driving behavior generation. It actually consists of three parts. First is that how should we construct the graph for a compact representation about the world. So here is an example in a driving scenario. We can see in this picture. And when we are considering the yellow circle car, how did it behave to enter into the intersection? It actually first cares about which areas a car can insert into. And then we can draw them on the picture. We can see it actually has several areas to choose from which area to insert into. And then we can actually define each area as a node like this. So each node has its information about this area. For example, the front bound car or rear bound car of the area. Then each area became a node. And next we can also define the edges between all the nodes. Then we can just reason about the relationship among each pair of the nodes, so that we can finally decide which area to insert into and execute the actions step by step. And with this graph construction, we propose a semantic graph network. It's actually a high-level policy that is take the compact semantic graph representation and generate an intention signal for the low-level policy to execute. And what did it do to achieve that? First is that it takes the semantic graph I mentioned above as the input, and each node is each area. And then we have the feature encoding layer that is pre-processing graph the temporal and the spatial information in each node. And then we have the spatial attention layer. It's actually reasoning about the relationships between the node. And this layer is actually handling the interactions between all the cars. Yeah, and the last layer we can have a prediction layer is actually based on all the information processed to generate a high level intention signal for the low level policy to execute. Yeah, and with this intention signal, we can actually send it to an encoder-decoder. It's actually a low level policy, which is executing the primitive actions to generate a whole behavior. And this encoder-decoder actually takes the intention signal as the input and also the historic dynamics of the car as the input. So in this, we can see the difference is that under this representation, the car only cares about its own historic dynamics, and all the interaction or other traffic rules are handled on the high level policy. So in this policy, it only cares about how to execute the action with a command, so that this learning can be very pure and maybe more efficient. Yeah, and and also notice that this encoder-decoder is also adaptable, because when we have the historic behaviors of the cars, we can actually infer how they drive in terms of such as driving styles or driving preferences. So with this information, we can actually adapt the parameters in the networks so that we can generate more accurate behaviors. And then we have some case studies. We can see this is some preliminary results. We can see on the left, the black car is the car we are caring about. And when it's entering the intersection, it first cares about which area to insert into. In this case, we can see there are 2 areas to insert into. And the color actually means the probability to insert into each area. And at this time, the probability to insert into each area are pretty equal, because this information from the velocity and also the distance. But later we can see as the black car accelerates, and then the probability converges to the area in front of the blue car, so that the black car actually insert into that area. And also we can see how the generated behaviors with the here of the 2 cars with the intention signal. And also we have another example. It's much more short. And at the very beginning, the car thinks that the black car is maybe yield to the blue car, but next it actually accelerates. Then it will insert into the front area of the blue car. Yeah, and these are some preliminary results. And for more comprehensive experience, such as how to design each networks and how the method performs in the transferability and adaptability, and also how they outperform other solver method, please expect our incoming paper. Yeah, thank you.
Okay, great. Thanks all the speakers. I will now stop recording.